So yeah, so this talk was based on a joint work with Brakkee. Yeah. Grossi. So, and indeed I will be talking about analogues of Hyperkähler manifolds, but the singular ones, and I will define it later, and we'll call them irreducible symplectic varieties. So, yeah, maybe before I start talking about the singular case, let me give you some motivation and explain something about the small case. So the first thing I want to start with is the more composition theorem. And what does the theorem tell us? So let's say I'm a compactified manifold. Or you can think about projective varieties, small projective varieties if you want. But this holds for other as well. With the trivial term class. Then there exists finite element of the following form. So I will tell you what these things are in a second. So let's say to n, where T is just a torus, yi Arbarello, and xi is as an irreducible homomorphic symplectic manifolds. Sometimes we is IHS. So sometimes people also call this these xi's Hyperkähler manifolds. And okay, we all know what a torus is. So these ones I will not define, but there are some class of manifolds. And these ones are the ones that we will be interested in. And somehow one reason why they can be interesting is because they're these building blocks of varieties with the trivial Chorn class or trivial canonical bundle. So, right. And this is in the smooth setting. And let me, since we will be trying to generalize this, let me give a definition of Hyperkähler manifold or irreducible symplectic manifold. So, it's irreducible holomorphic symplectic manifold if M is simply connected and F0 of x down to x is equal to sigma, where sigma is the holomorphic symplectic form. So, you see that the words holomorphic symplectic come from the fact that there exists this holomorphic symplectic form. And for example, well, I said I wouldn't write the definition, but for Calabi-Yau's, there's no such form. So, actually, I think this H0 will be 0 by definition. But yeah.
I'm still trying to understand the decomposition theorem. Can you somehow explain a tiny bit what it means to have a finite examen?
So this is just finite covering. So
okay, that's what it is. Okay,
sure. It's just this.
Like the pancakes.
Yeah.
No. I missed the word covering. No,
yes. Yeah. So yeah, finite Isle map. This is small, complex things. So this is just finite cover.
I have a question. If M is defined over Kuba, so at the closure of rational numbers, can T, Yi, and Xj define over Kuba?
I don't know. Does Kähler make sense over Q-bar? I don't think so.
I don't know.
Well, I mean, maybe there are definitions, but not that I know of. I think for these things, it's when you talk about Kähler geometry, it is very important that things are complex. But well, I mean, yeah. So some properties. Some easy remarks that the dimension of M is even, and the top extra power of the holomorphic forms on M is trivial, so canonical forms. Okay, and what are the examples? Kind of the problem is that there are not so many examples known of these objects, and just kind of going back to the classification theorem. So, well, for tori, there's not many things you can do. It's not hard to. There's no classification problem involved. For Calabi-Yau's, I haven't studied that much, but my impression is that there are too many examples, and maybe there are like questions of finiteness of examples, like in some dimension or something. But for reducible holomorphic symplectic manifolds, the problem is the opposite. There are not enough examples, and one of the things that people are trying to do is to build examples. So let me tell you all the known examples. So,
can do you have the word irreducible? And so like in the definition of IHS, irreducible, it comes like from simply connected. Yeah.
Yeah. Also, maybe, so I'm not sure like exactly how it goes, but maybe it also comes from the fact that this space is one-dimensional, because maybe you could have more. Yeah, because I think if you take product of two things, then, but anyway, so I don't want to say anything wrong, but yeah. So let's do some examples. So one example that probably a lot of you would know is K3 surfaces. So this is dimension, complex dimension. So in dimension 2, Calabi-Yaus and irreducible holomorphic symplectic manifolds, I guess, are the same thing, and the only example is K3 surface. And some examples of how to construct K3 surfaces is one thing is a smooth orthic and check using a junction that the canonical bundle is trivial. And another example that probably everybody knows, or often one of the examples that is ramified double P2 with the branch locus a smooth sextant. There are more examples. There are more ways to construct K3 surfaces. For example, you can take 2-3 complete intersection before, or there are other ways as well. But let's keep going. So the other examples that there are two infinite families of irreducible holomorphic symplectic manifolds. So one of them is S. So S is a K3, any K3 surface. Then this is Hilbert scheme points and points. Right, so, or if you don't know about Hilbert schemes, you can just take a symmetric product of n times the so you can resolve a symmetric nth power. So this will be singular, but then you resolve it, you get something smooth, and this is the Hilbert scheme of points. And you can do it for any n. And there's also so-called generalized Camere, and say A. So this is generalized Camere, and you construct it from an Leuven variety, on a given surface. And give you the construction here, but this is also an infinite family, and you can do it for any n. So kind of we got two ways of constructing irreducible holomorphic symplectic varieties, but question is, are there more? So except these two families, there are only two known. There's the exceptional examples of Grady, so Grady 6, and so what G stands for already. And already is the person who found this, and he found this example by resolving modular spaces of shapes on K3 surfaces, and I will mention a little bit about that later as well. And everything else that is known so far, all known examples are deformation equivalent varieties. So deformation equivalent just means that you can put things in a small family, and yes, the central fiber is the thing that you start with, and then the complex structure deforms, and things happen. And yes, so in what I will be talking, maybe I will tell you. I'll write it in more detail later, but okay, so there is a singular generalization of the Bogomolov-Yau decomposition theorem. So there's a singular due to inverse version and Thomas Becker. In their singular analog, the statement is the statement will be slightly different. So you will be allowed to start with a singular variety, and then you will have the torus will still remain the torus, and for yi and xi you will need to give different definitions. But essentially, a very similar statement holds, and the goal of the thing that we did was to construct not the smooth examples of Hyperkähler manifolds, but the examples of the singular analog of these Hyperkählers. So there's still not so many constructions known, but it seems like they're much easier to construct, and since there's this analog of the Bogomolov-Yau decomposition theorem, it's also interesting to study them. And so
Mr. Midt, most things you have really just works for me, like including the compactified manifolds, but you said imagine a projective.
For a complex projective smooth.
Okay. So, so you say, did you take this general sort of classification theorem as an incentive to study the blocks which appear on the right side, there, the axis?
Yes. So
and you want to understand them better and list examples to this. Now, the building blocks here, are there examples all of T, Y, X? Are these particular cases of compactified manifolds?
Okay, so examples of xi's here?
Well, no, I mean in general, does this basically say that if that anything which is covered by any such product is a compactified manifold? Is that also implied? Are these is the torus a compactified manifold?
I mean, if you get something smooth, then yes.
Okay, and the IHSs also there are cases of compactified manifolds.
Yes. Yes. What follows later, everything will be projective. So I just used compactified manifolds because this holds in this generality. But so everything here is compactified. Or if you start with a projective, everything will be projective. And right. Does this answer?
And this extra condition C1m equals 0, they also hold for all those.
Yeah. So this. So when people work in algebraic, like not in the complex geometry setting, but in algebraic geometry setting, they often talk about K-trivial varieties instead of varieties with C1 equal to 0. So the canonical class is trivial. So that's something that
K-trivial. How is it called then?
K-trivial.
K-trivial.
So if that's something that's I'm used to, but yeah, but I will.
Maybe we should add that so this is the is a topological invariant of the tangent of this. It says how simple, you know, you step in a point, you look at the tangent space, how simple this thing varies.
This C1M.
Yes, yes, it's I mean, it's yeah, it is this tangent value and spits out a topological class that somehow measures how simple it is. And this is, yeah, so when it's negative, it's very simple. This is the first step.
So, yeah, so this is, I don't know if you, I don't know what the background is, but for example, I don't know, again, in algebraic geometry, people usually measure the Fourier dimension of things, and then they're like Nestor said, you start with like negative, and then it's easy. Well, not so easy, but easier than the rest, and then there's Fourier dimension 0, and then it increases, the things become of general type, and these are the ones that are very hard to study. So, and this is somehow in between of, in terms of difficulty, or roughly speaking. Okay, so this was the introduction. So, any questions about the motivation? Anything else? So I will be more concrete from now on. So, okay, so let's. The first thing that I want to mention. So the next thing I want to talk about is modular spaces of sheaves on K3 surfaces. And you can see. Oh.
Yeah.
So, okay, as I just erased, the K3 surface is just an example of Hyperkähler manifold, that this irreducible Kolmogorov symplectic manifold in dimension 2. So it's a complex surface. And the modular spaces of sheaves on K3 surfaces are very well studied. And from now on, I mean, you still can do it in the Kähler setting, I guess, but from now on, let's assume that everything is projective. So from now on, for the rest of the talk. Everything is a projective, it's a complex projective. And okay, so we'll be looking at modular spaces of coherent sheaves. So sheaves, so let's say that F is a coherent sheaf. Let's fix one for now. So in most of, so we will be talking about modular space of coherent sheaves, but for most of the time it would be enough just to understand what is a line bundle. But for now, I'll just define things for coherent sheaves. So there is a so-called chi vector of the sheaf, and it is an element in, so let's say my K3 surface, I define it as S. So S is the notation for the K3 surface. So, and this is H0, SC, plus H2, SC, plus So somehow we will fix this invariant, this Mukai vector, and we will consider the modular spaces, the modular space of sheaves that have this fixed invariant. So I haven't told you about this invariant yet. I just said that it's inside the space, and so there is a very kind of, you don't need to understand this definition. I will write it, but so first is the rank of F. So I mean we understand what the rank of vector bundle is, and you can define it for sheaves as well. Then we have the first term class of F, and then we have first term class of F squared over 2 minus the second term class plus rank of F. Okay, so this is some definition. So this is Mukai vector. This is how the Mukai vector is defined. And okay, and in our case, in the future, all this invariant will be more understandable. So let's not focus on what all these things mean for a different sheaf. So we want to find modular space of sheaves with a fixed Mukai vector V of F. We will need to fix another thing to define this modular space. So we also need to fix ample class H in so this is the so-called polarization of this. This polarization. So roughly speaking, the idea is okay. We can, for example, if we look at in the simplest example, for example, we're looking at line bundles. So and they seem like nice objects. But then if you just try to add all the coherent sheaves possible, then maybe the space that you get is not super nice. So we need to look at so-called stability conditions. So we need a nice way to compactify this modular space. And this is why we need this polarization. And I will not talk much about it. So actually, it becomes important at certain points, but let's not focus on this too much at the moment. So, and let's say, so the modular space.
I have a question. Need H to be primitive.
Say it again?
Need H to be primitive.
No, just ample.
Oh,
For now, it doesn't matter which. So in some cases, V will need to be primitive, but I will mention that in a second. So we're looking at the H. So this is the modular space of H semi-stable sheaves. With the Mukai vector V. And this modular space is not empty. If and only if W squared is greater or equal to -2. And W, I can define what W was. V is KW such that W is primitive. as mentioned. So indeed, the primitivity is okay. So what is primitive? Primitive just means it's okay. It's an integer here, and primitive just means that you cannot divide it by an integer that's not 1 or minus 1. And this space has nice properties. I mean, independently of all of your choices, it is, for example, compact. And moreover, it's so I'm regular. It's symplectic. So there's so this is a nice space. It is not always smooth, but the regular part is the locus where it is smooth. There is a homomorphic symplectic form. And moreover, so okay, let me check here. So let me just actually check this compact. Symplectic, and this irreducible homomorphic symplectic manifold is smooth. And it turns out that actually, if it is smooth, then it is of type S n. So of type Sn means that it's not necessarily is a Hilbert scheme of points, but it is deformation equivalent to the Hilbert scheme of points. And kind of this shows that if the space is smooth, we don't get anything new. I mean, it's a nice construction, but kind of the result is slightly boring because we didn't receive any new examples as we wanted. So it's more interesting and similar. So
cookie one. We arrange.
That's not the weather for ice cream. Anyway. So you said that the okay, this is distracting. So you said that the regular part is symplectic. Like what happens? Can you say what happens with the symplectic form when you reach the singular part? Does it blow up or something like that?
So I will talk a little bit about that later, but it is still, I think, okay, so maybe we need some very mild assumptions, but I think no, I'll double check in a second that actually it is a symplectic variety, and I will define what a symplectic variety is. But symplectic variety means that if you resolve the singularities, that you can extend the symplectic form, but it's not necessarily symplectic, so it can get zeros.
Okay.
In this slot. But this will come up eventually. So some examples. Yes, so if I take b equal to 2, 0 minus 2, so very concrete, we get that m be h singular. This is because this is non-primitive. So kind of if your thing is non-primitive, you usually get singular things. But in this case, it is good that but you can resolve and get this one of these exceptional examples of radial 10. And can also get already 6. I don't remember which you need to write, but these are the only. This actually the only 2 examples that you can get from this procedure. Turns out. Okay, and in general, the moduli spaces of sheaves on K3 surfaces with V non-primitive and a generic polarization. Generic just means that all the semi-stable objects are actually stable. So this is something about the polarization. So if for almost, let's say for almost any polarization, if V is non-primitive, then your variety is an irreducible symplectic variety, which I will define soon. So this is our analog of Hyperkähler in the singular setting. But in general, they will not have symplectic resolution. So they will only have symplectic resolution, which is like Hyperkähler, like only in 2 cases essentially. So, all right. So we get mostly singular things. So and smooth things that we get from this construction are just to repeat, Hilbert scheme of points on K3 surface over A6 or over A10. So and now let's get into the singular setting. So I told you that the Bogomolov-Yau decomposition theorem exists for a singular setting. So and let's this is an important definition. So, first definition I want to give you is symplectic variety. So let's first of all fix that X is will always be normal, projective, normal variety. Okay, and let me also say that X regular is the smooth locus. This is just a notation so far, so I don't define anything. And this is the smooth locus, and we say that this is so-called sheaf of reflexive forms. This is just the push forward via the inclusion of the regular locus. So this is the so-called reflexive forms. And they're called reflexive because this is actually isomorphic to so this very reflexive, and this is kind of the types of forms that we will be working with. So okay, our thing is singular, so we can't really make sense of symplectic form in general, but we can make sense of symplectic form in the smooth locus. So now the definition. So first thing I want to define is the symplectic variety. And this is the definition through Bondwell, it's 2000. And it is called symplectic if it has a symplectic form sigma inside of omega 2x. So this means that this form is symplectic on the regular locus, because these forms are the ones that come from the regular locus. And secondly, every resolution of singularities from x to the x, the form sigma regular, which is sigma regular, extends to a homomorphic form So this is exactly what I replied to your questions in words. So, okay, we just wanted to extend to a holomorphic form and can have zeros. And if it actually extends to a symplectic form, it's usually called symplectic resolution, but these things are very rare. So you would know, at least in this setup, you would almost never expect that this would happen. So we will have symplectic varieties, but normally we will not have symplectic resolutions. And so this is not the analog of the irreducible holomorphic symplectic manifold yet. So there will be one more intermediate definition, and the third one will be the analog. But essentially, you can guess these definitions. You just take the definitions from, for example, you get the definition of irreducible holomorphic symplectic manifold, and you just replace the usual forms with these reflexive forms. And that's more or less it. So part 2 of the definition is called so-called primitive symplectic varieties. So a variety is primitive symplectic if it is symplectic. So definition 1 plus h1 of x for x is trivial, and h0 of x and x is generated by C. We kind of, so we're primitives, so we don't want any other symplectic forms. So in the previous definition, we could, in principle, have more forms. And so in part 3 is the definition that we actually care about is irreducible symplectic variety. It is a primitive variety plus the following. For every finite quasi marking from variable x. So y doesn't have to be smooth here, and quasi-tal means that outside of a quarter-dimension 1 locus, this is a finite cover. Then omega y. So let's also say that the definition of y is equal to 1. Then omega and y is spanned by this reflexive pullback. It was a bit long, but so basically for Hyperkähler varieties, these holomorphic forms are actually generated by the holomorphic symplectic form sigma, And here we will want to generalize this definition somehow. So, yeah, and we replace, and we also don't use the resolution, but we want it to happen for every. Okay, so these are the definitions, and this is the analog of irreducible holomorphic symplectic manifold that we will be working with. And I mentioned before that there is this theorem of Corin and Paternal that talks about this components, these building blocks in the decomposition, and the third building block in this decomposition will be exactly the same. And the object that I will describe soon we will be trying to prove that it is an irreducible symplectic variety. So, any questions so far? Yeah.
Yes, I don't know what a symplectic form is, but my question is rather like, what is this part of the data, or is the symplectic form, whatever it is, unique, or how should one understand the sequel if a number I just has a symplectic form and sigma is not unique?
So sigma, so in kind of in the case that we're working with, sigma will be unique. I mean, up to multiplication by constant, but essentially unique. And
so that means.
And symplectic form, maybe I don't know. The definition is just it's a non-degenerate form. So it just gives you a non-degenerate skew-symmetric matrix at each point if you plug in vectors.
An alternating form.
Yeah. Okay. So it is an alternative form, and this matrix is non-degenerate.
Okay, and so basically it's not really unique, but whatever you say, the sequel doesn't depend on which one you pick, which sigma you pick. Just that it exists.
So in part one, it exists. Just we can choose sigma such that this happens. In part two, it assumes that okay, it is symplectic. So part one says there exists such sigma. In part two, it says that turns out that the sigma is unique. So I should probably write C times sigma. So it is generated by sigma. Part two makes sure that it is unique, and part three also tells you something about not just the second reflexive forms, but the whole reflexive algebra. And so in this reflexive algebra, just because in the definition you can just think about this as forms on this regular locus of X. So here sigma generates holomorphic two forms on the regular locus of X. Here we require that, well, I mean, it's a bit more, but in particular that sigma generates the holomorphic, the whole exterior algebra holomorphic forms on X, regular.
So, and this thing is that for all of them then, so it's independent, like, okay, a symplectic variety is a variety that has a symplectic form, right?
Yeah, and
but they can have several, and then you're saying that all of them extend.
No, so maybe yeah, this maybe was a bit confusing. So here, so in this part, sigma is already fixed. So maybe there is another symplectic form for which this does not hold. But yeah, you're right in the sense you can say that symplectic variety is three-stage. So it's a pair of X and sigma. So a priori there can be many, but when we're talking about symplectic variety, we fix sigma. So symplectic variety is a pair of X and sigma.
How would you go about checking the last condition for every quasi-atomic something like that? Sounds tough.
So I'm hoping I will even be able to say it in this half of the talk before the break. I mean, the answer is that we are not actually checking this condition, but there is we're checking two other conditions that apply this condition. Okay, so I have 10 minutes before the break. So let's see what we can do. So, okay, so maybe let me announce that, okay, we provide a construction. So I will describe probably in the second half already. So it gives you, so the construction starts with S K3 surface and I antisymplectic involution. So Z2 action, antisymplectic means that it so let's say that we have X sigma now. So remember K3 surface is a holomorphic symplectic manifold, reducible holomorphic symplectic manifold, so K3 surface comes with the symplectic form sigma. And so we start with this data, and this will produce us symplectic variety P. Actually, there is also involved in Mukayan vector and polarization, UAP, and it will be a candidate for reducible symplectic variety. And we will, well, I haven't told you what it is yet, but we will provide criterion like on the construction involves more data, so it's kind of conditions on the data that we're starting with. So for example, K3 surface should be general, and there's some, since, okay, so there's B and H, there should also be some conditions on B and H, but this is what we will be doing, and then how do we do it? So maybe to answer the question before we take a break. So how do we check? There is the following theorem, which says that if so I don't make mistakes. What was this? So, okay, there's a theorem that's not our theorem. Well, I mean, in this statement, okay, the exact statement that we have in the paper is our theorem, but it is essentially written in paragraph in 23. It says that if P is a symplectic variety, so just the first definition, and the two things hold, and first there exists dominant rational map on M to P, where M is an irreducible symplectic variety. So symplectic variety is the definition A3. And the second is that A1 P reg 0, then P is an IC. Okay. So I haven't told you what the construction is, but so the things that I will do in the second half, I will give you the construction of P, in more detail, and then we will do these first things. So part 1 is actually pretty easy, and part 2 is hard. Yeah, so part 1, you essentially just take the K3 surface that you started with, and if you take the nth symmetric power of this K3 surface, you can map it to P, and well, symmetric power of a K3 surface is a nice V, because you can even resolve it and get a Hilbert scheme of points on the K3. And then for this, I don't know how much time I will have in the second half to say anything about this, but kind of the main bulk of work is this part, but somehow also it's very topological and a bit different flavor from the rest of the paper. Okay, so I promised I'll give you an instruction, so we'll speed up a little bit this half. So what is the instruction? So well, you have a K3 surface as sigma. So sigma is the symplectic form of the K3 surface, and we have an antisymplectic involution. Again, antisymplectic in that sense, and we require that the K3 here is very general. What does it mean? By definition, it means the following. It just means that where's the definition? Okay, so it just means that H2 S C invariant is equal to the so kind of all the algebraic classes on S are actually invariant with respect to this antisymplectic involution.
What's that symbol on the right hand side?
This is the neuron-Sever group S. This is H11 S.
Thanks.
Okay. And so we require it to be general. Okay. Now what? So what is the, so this is the definition. So what is the rest of the data? So we fix C, smooth curve on the quotient surface. So fact, this is due to an equalian, and there are more things to say about this, but let's just for now assume under this that T is smooth, and there are two cases. If involution doesn't have fixed points of this and Enriques surface, you can treat it as a definition of Enriques surface as you want. It's a quotient of a K3 surface by an involution that has no fixed point, or it is a smooth rational birational to P2, and yeah, like just to emphasize, it is if you have such a general K3 surface, and if you have antisymplectic involution, then the quotient is always smooth, and we fix smooth curve on this quotient. Moreover, assume D. Okay, so let's say F, so notation is the quotient map from S to T. Assume that D is the F inverse C is smooth. Essentially, if you you have a smooth curve in T. If you move it in its linear system, then you can show that you can find D such and smooth. So it's not a big assumption. It's a very mild assumption. And another piece of notation: B is in T the branch locus. So for Enriques, it is empty, and B is, again, the computation. B is just, since it's a ramifiable cover, B lies in the linear system of the canonical divisor -2 of the canonical divisor T. So, okay, so this is the setup. Let's just remember that we fixed all of this. Now, let's remember that we talked about the modular spaces of shapes. Let's say M is MVH. So H, any polarization for now, and V means something specific. V will be on the form 0, D, 1, minus Q. So let's look at it for a second. Okay, we're talking about modular spaces on K3 surfaces. So, okay, we have this quotient T, but this modular space is of sheaves okay. So, I defined Mackay vector before, and it was something with strong classes and stuff. But what do these things mean here specifically? So here they have very simple meaning. So it means that this is the rank of F. It means that the sheaf is supported on a set of codimension 1 or less, which means that most of the points the strokes are 0. This means that D is the support of F. So of course this is the cohomology class. So well, maybe not D is the support of F, but some D0 in D is some curve D0 in D is the actual support of F, and this is just the Euler characteristic of F, or equivalently it will be the same as 1 minus genus of D, where D is the support. But if you want to define Euler characteristic for sheaf, you can just write a resolution by locally free sheaves and then define the Euler characteristic by adding and subtracting Euler characteristic of other things in that sequence. Okay, so here it has a very concrete meaning, so we don't really need to think about the initial definition. So we'll be looking at these specific things. One thing to notice, one thing to notice that this doesn't have to be primitive, or like D is will be divisible by 2 because it's a pullback of curve downstairs. So this we expect to get something similar. So how to think about this space? So okay, this is just something with the coherent sheaves, whatever. So, but we can treat this M, this modular space, in some sense the relative Jacobian space. So what do you mean? So I mean, this is maybe not exactly an appropriate name, but let's see. I will say where it goes like this. So relative Jacobian. called. How does this map look like? How to understand this modular space? Well, I claim that if D and D is reducible, then we have the following. Then we have that actually F sheaves supported on D are of the form let's say D is included in S, so the sheaves are of the form push forward of L, where L is a line bundle. Okay, so I mean this again, maybe a bit of a black box here, but if I'm just to repeat, I'm claiming that really this modular space, if I restrict, so this map is of course the support map. So if I take a sheaf and I send it to its support, I get this support map. And moreover, if I take an irreducible curve in this linear system, then the pre-image of the point here corresponding to this curve is just the sheaves that are push forwards of line bundles on D, which means that that phi inverse of D is the Jacobian. Okay, now maybe not necessarily 0 depending on the degree, but the line bundle on D, Jacobian of D. Okay, good.
But then why does it have to be a line bundle?
Sorry, maybe here also. So reduced and reducible. So, no, because I mean, I think it is somehow hidden in this color characteristic part. So this, if you say it in words, it should be modular space of rank 1 pure sheaves something. I don't remember the exact term, but it is hidden in this Mukai vector. So this Mukai vector has rank, degree, and okay.
No, it's the fact that this.
Sorry.
I think it's the fact that this integral, because if you have a vector bundle, no. Okay, sorry.
No. Yeah. So I got. Right. So this is one part. So we have this map, and now, well, as promised before, we extend the involution to this modular space. So we have this modular space MVH, and there are two involutions. on M, on the H, and one of them is just the one that comes from the extension of I. So we have I star from M to M. So M acts, I acts on S, right? So it takes, you just literally take a pullback. So it acts on S, so you have one curve is mapped to another curve, and you take a pullback of the line bundle of this curve, shift from this curve to this, the shift from that curve. So this is actually, I do not claim that this is a regular map, it's a variational map, because I just told you how to define it for integral curves, but I didn't tell you how to define it for other curves, because this explicit description of the shifts is just for the integral curves. So second thing, we can define J from M to M, and again, it is not necessarily a regular map, and it is sans F. Shift form F between from F to 4S. Okay, this is just taking the dual shift. And then we define tau to be a composition of J and I star. And let's see for a second. So you can check. So some things, okay, this is something that I already said, that this M has a symplectic form. Moreover, you can check that with respect to the symplectic form, both of these involutions are antisymplectic. Maybe we'll have a discussion that M is a symplectic variety and it's not smooth. So both of these are antisymplectic. In particular, tau is symplectic. Because, and also you can check, well, for this you don't need to know anything about the symplectic form. You can check that J and I star commute. Because, I mean, one is taking a dual, the other one is taking a pullback. I mean, at least they commute on the integral things. And kind of the point is, we can always only think about okay, so we have the symplectic solution, and we want to look at the fixed locus of this involution. And okay, there's some problems. It is just a rational map and not a regular map, but you can take a fixed locus, for example, just for safety. We'll also need to take the fixed, the component of the fixed locus that contains bundles of the form iota star 40. So this is how we define fixed zero of tau. But it will turn out, I mean, I'm not going to explain it, but actually it turns out that there's just one. If you're not talking about Enriques, if you're only talking about rational surfaces, then there's just one component. So this zero is not strictly necessary. But in the Enriques case, there are 4 components.
We decide like one of them acts on the fibers, and so the I star exchanges 2 fibers.
So I star exchanges fibers. This one does not exchange fibers.
This one acts on each fiber.
Yeah.
By -1.
Mm-hmm. Yeah, so this one acts by -1 on each fiber, this one exchanges fibers. And the fixed locus, let's go. It's fixed locus, P, let's Okay, so since it is a rational map, let's say that it is the closure of the fixed locus inside of M, because this lies inside of M. So and we have this map from P to C, which naturally sits in D. So, I mean, of course, C and D are different linear systems. D is a double cover of C, so kind of you can embed this here by just sending C to its pre-image. Right? Okay. So remember, we had this double cover into C.
It's like 1/2 C.
Hmm?
It's like 1/2 C. So then we put.
Yeah.
That's,
Yeah. No, but I mean, if you just think about it as like sets of curves, like, I mean, normally when I think about it, just say, okay, this is a collection of curves, this is a collection of curves, and then I take pre-image and yeah. So okay, so this somehow naturally sits here, and there is a vibration from here to here that sends the sheaf to its support. And notice this, okay, this interchanges curves. So this, like Ignacio said, it's just like x is -1, but this one actually interchanges the supports. But if the curve is fixed by the involution, then the curves that are fixed by the involution are the ones that come from C. Okay, so this is almost the thing that we want to work with, except we don't know if this thing is normal usually. So we define PH to be the normalization. And because the problem is that in all these definitions that we use, we require normal, because if things are not normal, they usually don't behave nicely. So this is the construction. So first, there are a lot of things that I didn't tell you. So let me just address a couple of them. So first, any questions about this construction?
so wait, because when you say this is the construction in this PVH is an IVS. That's
I haven't claimed that yet, and there are some conditions, but kind of this is the thing that we will look at, and we will claim that often it is an irreducible symplectic variety. But there are some things that need to be said, because it's a priori it is not even necessarily a symplectic variety. And well, very roughly speaking, you can try to prove that it is a symplectic variety by, okay, taking an embedded resolution inside of M. So P sits inside of this modular space M, and you can take an embedded resolution, and then you can try to take the symplectic form from upstairs, but there are some issues with extending the symplectic form. So okay, I'm not saying this super precisely, but what I want to say is that we need that the polarization is very specific. We need H to be equal to D. In order for these things to work, you need H to be equal to D. And this is the question of extending the symplectic form. So this proof is a bit involved, so I don't want to go into details. But another thing why we want this is we actually want the involution to be regular. And if the polarization is invariant, then we can achieve that. Because if the polarization is not invariant, then how do you know that semi-stable things remain fixed and all that? So this is kind kind of crucial here. Because if you have a regular involution, there's a theorem, I think it is due to associated maybe, but anyway, if you have a symplectic, if you have a finite group acting regularly on symplectic variety, then the fixed locus will be symplectic. If you don't have a regular action, you don't have such a theorem, and it may turn out that it's not symplectic. And there's an example in the thesis of Julia Saccà where she provides example where the symplectic form does not extend. So this is important, but with this we get some problems. In particular,
wait. So you just said that you assume that the action extends.
I did not. If we assume this, then the action extends.
Does you claim that you did not claim? What you claim?
Sorry, I should write things instead of saying them. Tau is regular.
Okay.
The converse probably is not true, but tau is regular, and then we can use this theorem that fixed locus of a symplectic, if a group acts symplectically on finite group acts symplectically on symplectic variety, then the fixed locus is a symplectic variety. Thus, okay, but with this we get some problems. In particular, this polarization is not generic anymore. So H is not generic. And thus M is likely not smooth. However, M is still symplectic. And simply connected. So this we need for P to be symplectic, and this we'll need when we probably we will not talk about this today, but when you do simple connectedness, you specifically need M to be simply connected because you use some exact sequence from topology. I mean, the method is there's exact sequence due to Langman, and you need to do some work, but and if it is important that the fundamental group of M stands in that exact sequence, and we want this to be zero, otherwise things will not work. But thankfully things do work, so good. Okay.
But what is the variety that will dominate this grid? I mean, I thought you were. You wanted to use this theorem.
Dimension. Yeah, symmetric power. Okay. So you do not dominate it with M, you dominate it with this. And this I probably will explain. So, right, any more questions here? Okay. And so how do we go about the fact that it's we guess primitive symplectic? So okay, so the way I stated the theorem was that if it is dominated by an irreducible symplectic variety and that if it's simply connected, then it is an ISV. So now we're talking about the part that Ignacio just mentioned. So, okay. To show dominant map, dominant rational map, that one. So, well, we don't necessarily need to show this map exactly, but we will show that there is a rational dominant map of this form, and that this will conclude the first half of the proof. Okay, so now let me give a sketch of a proof. So there are things to be checked. In particular, okay, there are some computations involved, but let me roughly outline the proof sketch. So, okay, so we have this, okay, let's say that H0 of S D. Let's say that this is V. And the claim is that V is the direct sum of the two spaces. So far, this doesn't have anything to do with the statement. I mean, all this S and D, of course, from the setup that we had, but let me introduce some notation. So it turns out that this splits H0 as D, this V splits as desired sum. Let's see. So, and this is the -1 eigenspace of the action of I on V. And this is the +1 eigenspace. I'm skipping all the details, so maybe it's not super clear at the moment. But okay, and then we also say that we send this. So how does this map work? Okay, and the page that I want to look at. So we have a bunch of points. So this symmetric power is a bunch of points, say Z1, Z, okay. And we want this locus to satisfy, so this belongs to the symmetric power. And we want to look at the specific locus of these things. So we take Z1, ZK, must span, and C1, ZK, span I wrote it correctly. So this makes sense. Elaborate question a bit, so it's a bit hectic. So let me write this better. So this. Okay, so I will here construct some open subset in symmetric this symmetric thing, and I want this to, okay, so as you will see here, and I want to construct a rational map from here to here, but I want to construct it in a bit of a weird way. I want to, this will be a fibration over C, and I want to define this map, and then define this map using this map. So, okay, just bear with me for a second. So, both of these things will be fibered over C, while PVH is fibered over this linear system we already know. And this I haven't explained yet. So, okay, so I omitted some things, in particular that C will be embedded into EB dual via D. So again, we also will assume that these things are very ample. I didn't assume this in the beginning, but for this proof to work, we will need that. So C will be embedded in this, S will be embedded in this, and also T will be embedded by C, and actually B minus, where the plus and minus eigenspaces are these ones. So, in particular, this points in sim S. So we get a bunch of sorry. So is this part okay? Because like I feel like I was very hectic, so I'm not sure if like which parts are clear and which parts are not. So let's just okay. This maybe forget about that part for a second. Is this okay? So this is it clear what I'm trying to construct?
So each of these points imposes a linear condition on the linear system, and you are so imposing enough. A general point on a K3 imposes a coordination 1 condition on the linear system, and you are imposing enough so that you have dimension, I guess.
Yeah.
But the fact that this map is dominant.
I mean, okay, this is kind of something that I was not going to explain actually. So kind of one thing that I was going to explain is what you said. So that there is some way of constructing this, but there's still a lot of things to check in the sense that you need to, maybe it will be clear that it is dominant, like these two maps are dominant. Well, this is of course dominant, this is dominant, but kind of that it's dominant fiber-wise, it's something that needs to be checked, and it's not easy to be checked. Well, I mean, it is not hard also, but it's a computation, it's a thing to do. Okay, yeah. So maybe I shouldn't have attempted this, but yeah, very roughly speaking, it goes like this, and we can discuss afterwards if you wish. But maybe since it's almost the end of the talk, I should finally say the theorem, that the main theorem of the paper. The theorem is as follows. This will look a bit technical, but so we assume many things. Okay, so let's say we assume everything that is said in the setup. So we have this S, we have this double cover, and now we say that PD is IC. If this is not an if and only if condition, there are so first of all, C and D are very ample, and this is what you have seen in my terrible attempt to give this proof, is that we need this to be very ample because we need to embed S and T in this PV dual and PV minus, and then kind of we'll get a hyperplane and then we'll intersect it with this S. Anyway, it is necessary to be able to do this embedding. Secondly, C dot B is greater than 2. Thirdly, C squared is not equal to 4. Or C dot B, remember B is differential locus. So 4, C is 2 connected. And this is another technical definition, which means that if C can be, if curve C prime in C can be split as C1 and C2, then C1 dot C2 is greater than 2. And 5, C is not hyperelliptic. B squared is less than 3. So this, okay, so time is over, so I'm almost done. I'll just comment a little bit on this theorem. Okay, actually the important comment that I had to tell before, that the part of the, so for Enriques surface case, it was done by Arbarello, Saccà and Ferretti. And a few cases, a few very specific cases were done for rational surfaces were done by Markushevich, Tikhomirov, and some other examples by Matini. But our goal here was to do it under certain condition for all the rational surfaces. So this is one important thing to say. Second important thing to say, and if in order to construct this dominant map, you only need condition 1, and everything else that we have is actually to show simple connectedness. And this may look very, very ugly, but this is a kind of the numerical translation of the conditions where we want to say that, okay, the locus of bad things in the base space, so the locus of bad things in the linear system of C is small. So basically, we study loops that go around the divisors in this space. So that and we want the divisors of singular things to be specific, very specific. So we want them to have easy singularities, like one node, or maybe they can be smooth, but the branch locus is tangent to this. But if you don't, okay, these conditions are not optimal, but this is the one way we could translate the conditions to get the geometric conditions on the slow side. Yeah, that's all I wanted to say. Sorry for going 2 minutes over time. Thank you.